So the next speaker is Jagadheesha from his local, from here, not too far, right? From the ISRO headquarters, which are pretty much walkable distance from here. So he will talk about some observations on retrieval of geophysical parameters.
Occultation sensor is touted to be a very good climate quality data, and methods and usually GPS servo based either bending angle or refractivity are assimilated in the model using 1D wire or nowadays even 2D variational assimilation or 3D variational assimilation. So there exists other methods also which typically use surface meteorological parameters like temperature, mainly temperature and pressure, to derive humidity parameters. So my work is mainly to retrieve geophysical parameters from RO data without any additional parameters, but some observation based statistics. So previously I developed one method which used surface meteorological parameters, which was published in the Journal of Atmospheric and Oceanic Technology, and that I am referring as refined temperature method. I'll explain it later. And in the recent work I have detected water vapor height above which water vapor is practically negligible. So in a large number of diverse radiosonde profiles, radiosonde derived reflectivity profiles over the tropics. So just for sake of continuity, I am explaining what GPS radio occultation means. So we typically have a GPS space qualified GPS receiver mounted on low Earth orbiting satellite. So it receives signals from GPS satellites. So as it is moving, so it will receive from one particular GPS satellite, it will be receiving, the signals will be passing through different layers of the atmosphere. So as a result, bending takes place. So this bending angle is essentially what is measured, and which is converted to refractivity, and which in turn is related to geophysical parameters. So just I am showing the geometry. So steps involved in, there is a large number of steps involved in GPS RO data processing from GPS signal to refractivity. So just I am showing glimpses of that aspect. So it involves calculation of bending angle from excess Doppler, refractivity from Abel transform, and then conversion to atmospheric variables. So it is what phase path is defined like this: from GPS to LEO, N is refractive index, and DS is the path traveled. And if there is no atmosphere, then it would have obviously traveled the straight line path. So the excess phase is the actual path minus that straight line path. So rate of change of this excess phase change is what is known as excess Doppler. From this we usually derive bending angle, and from bending angle we get refractivity via Abel transform. So what is the horizontal resolution of these GPS RO observations? One can typically say, so the innermost layer contributes to more bending. So as you go away, so some sort of exponentially decreasing contribution is there. So some sort of weighted contribution you can imagine, and that way it is approximately 300 kilometers, you can say, horizontal resolution. And then what are the precision of these refractivity measurements? So one which came in 2008, the latest estimates say that they are indeed very precise. Precision estimates are within roughly, you can say, RMS N is within 5 N units in the lowermost troposphere. So within almost 1 to 2% error in lower troposphere, and the upper troposphere they are very precise. So the advantage of GPS radio occultation is that it is very accurate and high vertical resolution in lower troposphere especially, and it is all weather sounding capability. It doesn't depend whether it is day or night or cloudy or sunny, independent of radio sound or other calibration. So no instrument drift and no satellite bias. So measurement type is volume average as compared to point measurements of conventional radio sound and other data, making it ideal for comparison and validation with numerical weather prediction models and mainly for climate studies. And the retrieval process does not involve the use of initial guess profile. And I mean to say refractivity. Retrieving refractivity doesn't use any initial guess profile or anything like that. So these are some of the GPS radio occultation missions launched so far. So the latest coming will be megatropics, which is supposed to give dense observations over the tropics, approximately 700 soundings per day. So this is just some technical. So how would your GPS receiver, which is going to be mounted on LEO satellite? So what are the accuracy requirements of such a GPS receiver? So now coming to the main point of my talk. So refractivity to geophysical parameters. So refractivity, denoted as N, is retrieved from GPS RO sounding. It contains information on temperature, pressure and water vapor partial pressure. So operationally, cosmic and many other sites, they use 1D variational assimilation technique to derive temperature, pressure and water vapor pressure from refractivity. So there are techniques, as I said, which use surface or lower altitude pressure and temperature information to derive these parameters. So one is published in 2000 by O'Sullivan et al. And one by myself in JOT in 2009. So in light of 1D technique highly influenced by model forecast initial guess, it may be worthwhile to see how other techniques fare. For example, over land we have plenty of surface as well as radio sound observations. Whereas in deep ocean we do not have such things. So definitely models, how far we can test the model, we don't know. So now the problem is like this. So refractivity is related to pressure, temperature and water vapor by that equation, and we have hydrostatic equation for pressure. So we have 2 equations and 3 unknowns. So it requires either we should know temperature or pressure or water vapor for solution. So practically, generally temperature profile is used as solution is less sensitive to reasonably small errors in temperature. So if the atmosphere is dry, then we can use, then it will be water vapor is 0. 2 equations, 2 unknowns, we can easily solve. And it is practically valid above 10 to 12 km in humid tropical atmospheres. So generally the hydrostatic equation is initialized with climatological reanalysis or derived temperature at an altitude of 60 km. So the resulting error at around 30 or 20 km is very small. So I am showing just one typical dry temperature profile and actual temperature profile. So what we define as water vapor is this, where dry temperature is almost equal to actual temperature. So in the humid case, humid profile case, it will be somewhere around 9 km, 10 km like that altitude. So, but in some cases, in typically dry profiles, it can come down also. So how do we detect that in using refractivity profiles alone? That is the main point of my talk today. So the one method which was given by O'Sullivan et al. It basically estimates temperature as a quadratic function of logarithm of pressure. Sigma is logarithm of pressure. So we know pressure at surface. Pressure at water vapor point is known at around 10 km or so. Or when the dry temperature below troposphere reaches 230 Kelvin, that can be very safely taken as the water vapor point to begin with. So we know temperature and pressure at that altitude, and we have this hydrostatic equation. So using these 3 equations, we derive these quadratic coefficients A, B and C. So and then we iteratively solve these sets of equations to obtain temperature, pressure and water vapor pressure profiles. This is one method. So this typically shows how things are done with that particular. So to start with, in first iteration we take dry pressure, and then when we iteratively solve, they converge to actual temperature, actual or close to actual pressure and close to actual water vapor pressure. So I have studied this method also in detail on a large number of diverse radiosonde profile derived refractivity profiles. And the method seems to give reasonably good RMSE and mean deviation as far as water vapor parameters are concerned, that is specific humidity and relative humidity. So when applied on a sequence of radiosonde data over Bay of Bengal, it appears to give a bias. So when in humid condition, there appears to be a warm bias. So there are two options also. One is when we know refractivity close to the lowermost point. So another option is, in that case we have to approximate R with the gas constant for dry air. When we are knowing refractivity up close to the ground, then we can iteratively update that R and hence ABC as well. So there are two options for solving this one. So obviously in practice we can use only option 1 because we never have refractivity profiles reaching close to ground. So when in radiosonde we can try both the options. So in option 2 it gave 3 Kelvin error, and in option 1 4 Kelvin warm bias was there. So it shows that bias and RMSE are not uniform functions of profile and season in this method. So then I also developed one empirical method. So input for which is surface pressure and temperature and refractivity profile. So then we get dry temperature and pressure, estimate water vapor point, which I initially took as 230 Kelvin height when we look from tropopause and below. So then I get a crude estimate for hydrostatic term, that is 77.6 P by T in the form of log linear fit with respect to height using surface and water vapor point height P and T values, and then solve the following system of equations. We get pressure, temperature and water vapor pressure. So this particular is known as some first cut retrieval. So average of linear fit using surface and water vapor point height and this first cut retrieval is what I call as refined temperature. So using refined temperature and refractivity profile, you get pressure and water vapor profile. So this is the typical example where these symbols denote actual temperature. So this is the first cut retrieval and this is the linear fit, and this average fit of these two is the refined temperature, which is closer to actual temperature. So this is the statistics which show that refined temperature is indeed a very good approximation on over 3000 radiosonde profiles for the process. So this is the typical RMS in temperature, specific humidity, pressure and relative humidity. So as far as humidity parameters are concerned, the results are almost similar to 1D variational technique, and errors are within 5% for relative humidity. This is for all sorts of profiles including dry ones, and if we take humid cases only, somewhat improved humidity parameters we are retrieving. And these are some examples. Just skip. So this is when we have radiosonde, GPSRO based refractivity profile and 1D whereas all these things we are comparing, and we are getting almost similar results with 1D where using my technique as well as O'Sullivan et al. Technique, and so they are giving almost similar results as far as humidity parameter is concerned. So now next, can we detect water vapor point height below 230 Kelvin whenever the atmosphere is dry, automatically without using any input? So for this I used the refined temperature method. So in this case what I did is, so I varied the wet component of refractivity in lowermost altitude and detect the 3 reference profiles that are explained below. First one is, so when we vary the wet component of refractivity and solving it using the refined temperature technique, so we get one temperature profile which is just greater than dry temperature, that I denote as K dry. And then K wet, profile which has relative humidity in the range 0 to 100%, which I call valid range, and I denote it as K wet. And profile with mean lapse rate between lowermost altitude and 230 Kelvin, dry temperature high 6.5 Kelvin per kilometer, which is generally the average lapse rate which is observed in tropics. So then I set some selection rules. So if K dry is greater than 6.5 Kelvin per kilometer and K wet is less than K dry, then actual temperature profile is closer to K dry. So that is atmosphere is typically dry. So if it is less, K dry is less than 6.5 Kelvin per kilometer and K wet less than K dry, then actual temperature is closer to 6.5 Kelvin per kilometer, at least in the dry part of the troposphere. So if K wet is greater than K dry and K wet less than 6.5 Kelvin per kilometer, then likely humid conditions and actual temperature is between K wet and 6.5 Kelvin per kilometer. So the correlation between relative humidity profiles is also used mainly to avoid false detection of water vapor point at lower altitude. Suppose I take K dry, then for next 20 things I just correlate and just average, so that it should not detect any false thing in lower troposphere. So this is one illustration. So this square symbol denotes the actual temperature. So when I am varying my wet term, so the first solution I get which is just greater than dry temperature profile, that I call K dry. And then in humid conditions it can give unrealistic relative humidity like more than 100% like that. So then I still vary. Then I begin to get between 0 and 100% relative humidity, that which I am calling as K wet. And then this is 6.5 Kelvin per kilometer. So in humid case you can see the actual temperature is somewhere between those two cases. So now then once I set those temperatures, then I compare with dry temperature. So if I found out a height where the difference is, absolute difference is within 2 Kelvin. So then the lowermost height where the absolute difference is within 2 Kelvin, I call it as water vapor point, where the atmosphere is, you can assume that atmosphere is almost dry. So I detected in 5040 profiles for tropics, and these radio sound profiles are typically used in retrieving infrared sounder also, retrievals from infrared sounders also. So in this case, so at water vapor point, I am able to get RMS within 0.85 Kelvin, and pressure, RMS pressure is 0.47 hectopascal, and mean bias, there is some minus negative bias is there, 0.11 Kelvin for all the profiles together. So this is radio sound temperature at water vapor point, and this is the retrieved. So we are able to detect water vapor point much lower than 230 Kelvin whenever the atmosphere is dry. So now consider typically dry cases, that is when K dry is greater than 6.5 Kelvin per kilometer and K wet is less than K dry. So in that case, RMS is 1.12 Kelvin and mean is minus 0.34 Kelvin, and pressure of course within 0.77 hectopascal and less than 1 hectopascal we can say accuracy. And the third case is where that standard profile is greater than K dry and K wet is less than K dry. So when the standard profile approximates the actual temperature profile. So in that case RMS is 0.7 Kelvin, mean is 0.11 Kelvin. So pressure of course is also 0.33, 0.2. These are just theoretical estimates you can say. In practice it can be slightly higher than 1. So now so what would be your relative humidity errors in the dry case with this simple estimate? So you can see that for lower humidities it works reasonably well. The radio sound and retrieved relative humidities are close. So in higher humidity cases, there is some scatter. This may be due to seasons. So I'm just trying to generalize all profiles which are for all seasons, all longitudes within 30 south and 30 north. So I'm further working on the algorithm to delineate all those things. So in summary, so water vapor height has been detected in diverse radiosonde based reflectivity profiles alone using certain assumptions. So temperature and pressure at water vapor heights are retrieved to a reasonable accuracy. So future work will focus on retrieving humidity parameter with this work as baseline. So thanks for giving me an opportunity to speak in this.
Look at the last plot that you showed. Can you say which regions are giving you the larger errors or larger deviations from the best fit line or something?
Yeah, that is typically when there is discontinuity in lapse rate, those kind of cases only.
Meaning like?
Your dry atmosphere typically up to say 500 hectopascal, and then suddenly the lapse rate changes. So in those cases, you cannot simply continuous linear smooth, you cannot have a smooth temperature profile, mainly those cases. And then some winter and summer distinguishing.
Where, I mean, you would expect more errors in the summer hemisphere or in the winter?
In winter.
Why would that happen?
Because I was trying to generalize overall these things just by this condition. That was the reason.
No, yeah, but why would there be more errors in the winter? Because apart from that, humidity creates more problems for you. So
no, winter I mean in the over ocean sometimes there will be humidity just below 4 kilometers, and suddenly the temperature will start varying differently.
So that is where there is a lot of convection and clouding. That be the region where
convective regions are typically easier. I just showed one sample profile here. This is typically probably convective region only. So where within very narrow ranges we can confine actual temperature profile.
So you are saying basically if you have inversions then you have problems.
Yeah, inversion region.
Currently we are using bending angle or reflectivity directly at assimilation. So what is the importance of retrieving temperature and moisture profile from the same data, and you have this much of error in moisture at a higher levels?
Not higher levels. It is at a lower level only. All profiles I am just plotting.
But right now we are using reflectivity directly in our models.
No, I think bending angle is being assimilated.
Yeah, bending angle we are also use.
Yeah.
So what is the requirement to retrieve these parameters, temperature and moisture? And again there are some retrieval error, then we will assimilate again, then their error will be more after the assimilation. So we are adding the error in two different steps.
Yeah, that's why I am trying to constrain where your actual temperature falls, and by that way I am trying to retrieve, and probably that can be used in models also.
Okay, one more question. In RO retrieval case, whenever I use data is starting almost from above the 4 kilometer. Above the 4 kilometer or 2 kilometer. Like
yeah,
this.
because your reflectivity is up to those altitudes only.
Sorry?
Yeah, that's why.
We
are able to retrieve on most of the cases 2 kilometers above or 4 kilometers above only. They hardly reach below 1 kilometer.
Okay, thank you.
So we'll start at 11 after tea now.